Another way to store data is by using a linked list. There are a couple different linked lists. We can have a singly linked list and a doubly linked list. But in this lecture and in this section, we are going to talk about a singly linked list. Now, unlike an array, which requires a fixed size, we can use a singly linked list, which can easily expand. The concept around a singly linked list is pretty simple, but with Rust's ownership and memory system, sometimes it can be a bit more complicated to create a linked list in Rust than in other languages. So let's take a minute to try and understand what a linked list is. So we'll say we have a node, and we'll say it is node 1, and we'll just give it a circle, that way we know it's a node, and we'll label it as a node. So inside of a node, we're going to have two pieces of data at least. So we can represent this as a struct, and we will say the name of the struct is node. And then inside of here, we're going to have our piece of data. So in this case, our data is going to be 1. And then we're also going to have something that is called next. So what next is next is going to store the information, so the memory address, to another node. So we'll say we have node 2. And we'll say node 1's memory address, memory adder, is 100 to keep it simple. This link right here is represented by the next value in our node struct. And then we will say our memory address for node 2 is 200. So next is going to point to this memory address of 200, and we know at that memory address is going to be this node that stores the value 2. So now we can point this node next value to node 3, and then we can point this node's value to another node 4, and then we have one more piece that we can point 4 to. So let's just go ahead and fill this out. So we'll say this is our next link, and we'll say this is memory address 300 and this is memory address 400. So currently what we have for node 1, if we looked inside of its struct, its data is equal to 1, next is equal to 200, which this points to node 2, whose data is equal to 2, next equals 300, and this is node 3, whose data is equal to 3, next equals 400, who now we point to node 4, whose data equals 4, and whose next equals, well, if node 4 isn't pointing to another node, which it's currently not, what would its next be? Well, in other languages, you would typically point this to something like null to denote that, hey, this is the head of the list. So in Rust, we don't have null, but what we can do is we can point it to none, because we can create an option inside, and it can either be some or none. So we can have it denoted as none. But now you heard me say that node 4 is the head. So we want to know where the head is in the linked list, because this is going to be the top of the linked list, which is going to be important for us when we want to add elements or remove elements. So node 4 is also going to have another struct, or excuse me, there's going to be another struct. And what we're going to have in this struct, and we'll just call this link, is going to be the head, which then will point to a link. And we'll see this, and this will be much clearer when we look at the code. But what this head is going to do is it's going to point to the top element in our linked list. So now that we have a general idea of how linked list works, let's begin setting up our own linked list. That way we can begin to see how the code starts to form. And we will begin doing that in the next lecture. Now that we have a good understanding of how a linked list works, we're going to take the time to begin creating our own implementation for a linked list. So the first thing I want to do is create a new lib. That way we can use test cases to evaluate our solutions. So I created a new lib, called it section 21. So we're going to want to go ahead and change into that directory, as well as open up the librs file. We can get rid of all this boilerplate code, and now we are ready to begin setting up our linked list. So the first thing that we want to do from what we saw in the previous lecture is we want to create our node struct. And we're going to have it over generic T. That way we can use any kind of elemental data that we would like. So we'll have our first element of type T, and then we're going to have our next, which is going to point to a custom data type of linked T. And remember, next is going to point to our memory address. So let's go ahead and create our custom type linked T, and we're going to give it an option, because if you recall, our head can point to a none. So with option, we can either point to some or to a none. So we want to use an option here, that way we can also point to a none. And we're going to give it a box that's going to contain a node T. And now we want to create our struct that's going to hold our head, which is going to also be our list. And we're going to have our head, which is going to be of a custom type link T that we just created here. So this looks like a good starting point into getting our linked list set up. So in the next lecture, we're going to take some time to implement some methods into our linked list. In the previous lecture, we went over how to set up our linked list. So now, in order for us to even begin to test our linked list, we need to implement in some methods on our linked list. So what we can do is create an implementation block on our list, and now we can start creating in some new methods. So we are going to create a new method. That way we have the ability to even create a new linked list, and it's going to return a self. And in here, we're going to say we want a list, and the head is going to be none. And that's all we have to do to create a new linked list. So that's something that's really simple to do. But now let's take it up a notch and let's create the push method. And push is going to take a self, and we also need the element. That way we can give our node some data. So now we need to say let new node equal a box, and we want to create a new box, and we want to put a node inside of our box. So we will say element is equal to elem, and next is self.head.take. And this is going to take the value out of the option, and it's going to leave a none in its place. because now that we have pushed in a new element, this is also going to become our head. So our head is now equal to our new node. So since we are mutating the list, we actually need to make this a mutable self, because when we push a new node in, we are updating this list here. So in order for us to be able to do that, we need to take a mutable self. And if we implement in a push, then we're going to also implement in a pop, which is going to be very similar. So since we are mutating the list, we need to take a mutable reference. And when you pop, you are going to return the value that is being popped. So since we are returning the value being popped, we need to return an option T. And so since we want to take the head, because pop returns the last element that was inserted, which is in this case is going to be the head, we can run our self.head.take again. But now since we're taking the head, we need to point our element that used to point to the head, we need to make that the new head. So we can take a closure, pass in the node, and say the self.head is equal to node.next, and then node.element is what we want to return. So now that we have implemented in these three new methods, we need to have some test cases to make sure that these are working correctly. So in the next lecture, we will begin creating some test cases in order to evaluate the functionality of our three new methods. Something that we need to do for our linked list is we need to implement the drop trait. So we can do that by saying impl t drop for list t. And the reason we need to implement the drop trait for our list is because the drop would be done recursively. So if you think about it, if we drop here, so let's say we drop 3. Well, 3 is going to then drop 2. 2 is then going to drop 1. Well, this sounds an awful lot like recursion. Well, imagine if we had a really large list that we're doing this recursive drop on. What could happen with a large list that is recursively being dropped? Well, the recursion could potentially blow the stack up, and that is really bad. So what we need to do is we need to do an iterative drop to avoid using the recursive drop. So for us to do that, we're going to need to implement in the drop method. And here we will say let a mutable link equal to self head.take. So take the head. And then while let sum, and then we'll say mute boxed node is going to equal our link. And then inside this code block, we're going to say link is equal to box node dot next dot take. So what we're doing here is we're going to do an iterative drop. That way we don't have any chance to blow our stack using the recursive drop that Rust would have done for us had we not implemented in our own drop. So that is just something that I wanted to point out that we needed to do in case our list ever grew to a large enough size where a recursive drop would have caused our stack to blow up. So in the next lecture, we're going to start looking at implementing in additional methods for our linked list. Now that we have some methods implemented in it is time for us to test them. So we need to create some tests. So we will say mod test, and now we will say use super, and then we just want to take everything that we have implemented in thus far, and now we want to create a test. So we will call it basics, since we are just testing our basic functions here, and we want to create a new mutable list since we are going to be adding and removing elements. So we will create a new list. So the first thing we want to do is check if empty list behaves correctly. So we will use the assert equals macro, and we will say list.pop, and if we pop an empty list, then we should have none returned. Now we want to populate the list, and we will say list.push, and we're gonna copy and paste this a couple more times, and we will put in 1, 2, and 3. And now we want to check normal removal by using a pop. So again, we will say assert equals, we will list.pop. We know that we get a value returned, some value. So since 3 was the last value we pushed in, we expect that to be popped. And if we pop again, we expect some 2 to be returned, since 3 is no longer in the list. Another test, we would say push some more values on, and now we want to say list.push 4 and list.push 5. Let's go ahead and check our removal again. So now we want to say we want to pop, we expect 5, pop again, we expect 4 to be removed, and now let's do exhaustive removable check. So now that we know that 4 and 5 are gone, let's just go ahead and pop the rest of them. So now we expect some 1 to be returned, and if we do it again one more time, with 1 no longer being in there, we now expect none to be returned. So let's just go over this real quick. So we're going to check to make sure an empty list behaves correctly. With a new list being created, we expect if we pop something that none is returned. We're going to use push to populate some values. So we want to then pop to make sure 3 was the last value we got pushed on, and then we want to pop again to make sure 2 was pushed before 3. Then let's push a couple more values on. So now our list should be 1, 4, 5. We want to pop and then pop again, so then 5 and 4 are gone. And now let's just make sure we can pop 1, and then if we pop one more time, we want to make sure our list is now empty again. So if we run cargo test, we see that we have an error, and it is saying we need to add a semicolon somewhere. Let's see if that is our issue. Cargo test, and we see that our tests were completed successfully. Our one test passed, which means everything inside of our test ran successfully, and we have no failures. So it looks like our 3 methods are running correctly. So now that we know that we have a functioning linked list, let's begin implementing in a couple more methods and also look at some unique use cases that we need to account for. An additional method that we can add is peeking. Peeking is a method that is going to allow us to get a reference to the element in the head of the list, if it exists, but peeking does not remove the value like pop does. So the key difference here between peeking and popping is peaking is going to give you a reference to the head. Popping is going to give you the value that was in head. So let's go ahead and implement this in to see what it looks like. So we will say peak, and this is going to refer to ourself, and we are going to return an option with a reference to the data inside of head. So we will say self.head as a reference, and now we want to map it and say node, and now we just want to return our node.elem. So .asRef right here converts from, let's write this out, asRef converts from an option t to option and t. So it's a reference to the internal value, which is what we want. Another form of peak that we can have is a mutable peak. So we can say peak mute, and this is going to be a mutable reference to ourself, and we will say option and mute t. And as you can guess, this is probably going to be very similar to what we just had, but instead of asRef, we will say as mute, and then the rest is going to be the same, where we say we're going to map it to our node, and we want to return a mutable reference to node.element. So let's do a cargo format to make this a little prettier. There we go. So now what we can do with this is we can come down here and we can extend our test cases. So we want to add a new test case called peak, and what we're going to do is we need to create a new list, and now we want to verify that our peak is working correctly. So using the assert equals macro again, if we list peak while the list is empty, we expect none to be returned. We also expect that to be the case when we do list peak mute. Now that we know that those are tested, we can push in a couple of additional values. So we will say 2, 3, 4, and 5. So now that we have some values in our list, we can start checking to make sure that our peak is actually returning what we want. So we will expect some, and then we expect a reference to 5 to be returned. And let's do this again, but this time with peak mute. And notice that we're still referencing the same 5 value that will be in our list, because peak does not remove the value. So that is also going to be a good test to make sure that our value is not being removed. So let's do another peak mutable, but this time we want to map. We want to map this, and we want to say the value. Let's just do something simple with it, like we want to change it to, let's say, 42. Well, now if we execute these again, if we run peak, we expect 42 to be returned. And then let's make sure our pop works fine. And now we would expect a regular 42 to be returned. So let's run our test cases, and we see that we have an issue here. Types defer in mutability, and this is on line 97. So let's see if it is wanting it to be like that. So our test case on the peak mute, we need to make sure that we specify that it is a mutable reference. And once we have done that, we see that our test cases, and I need to make sure our test runs. I need to put that there. Cargo test. We see that our peak test also ran successfully. So we successfully implemented in peak and peak mute onto our linked list. So now in the next lecture we are going to continue diving further into what methods we can implement in on a linked list. In this lecture, we will begin implementing iterators on our list. The first one that we are going to implement is the into iter. And by implementing the into iterator, we will define how lists will be converted into an iterator. And this is common practice for types which describe a collection of some kind. So let's go ahead and begin setting up the implementation for our into iter. The first thing that we're going to need to do is create a new struct called into iter over type t that is going to have a list that is of type t. So now inside of our list implementation block, we can come down to the bottom of it and we can say pub fn into iter on self, and this is going to return an into iter where we say into iter on self. So not much that we have to do there for this. But now we need to implement the iterator trait for into iter. So we can say impl iterator for into iter on type t. And now this is where all the magic's going to happen for the actual iterator itself. So we will say type item is equal to t, and then we will implement in our next method. And next is going to be a mutable reference to the self, where we return an option on our self item. So where we return our item here. So in here, this is actually going to be something that's really easy for us to do. So if you look at how we set up our struct here, we set it up a little differently than here. So this is actually a tuple struct, if you remember that from earlier on in this course. So in order for us to reference our tuple struct, we can, the first element, which is also our only element, we can say self.pop or self.0.pop. And that's all we need to do in order for us to get the value into our iterator. So we have one iterator set up. There's another iterator that we can set up called iter. So let's set up our struct for that one, and this is going to look very similar to what we just did. So it's going to be iter, and this time we're going to need to add a lifetime, and then also on our t. And the iter is going to be generic over some lifetime, it doesn't care. And then we can use a struct, a normal struct in this case, to hold the reference. So we're going to need to hold a reference. So next, and we're going to say option, and since it's going to be a reference, we need to specify the lifetime. So that is why we have a lifetime attached to this struct. So when you have a reference in your struct, remember, you need to specify the lifetime of that reference. And now we have our iter struct set up. So now we do the same thing again. We come down below our into iter, and now we're going to set up our iter, which is going to, again, be a reference to our self. And again, we're going to return an iter t, which is going to return an iter struct, where we say next self.head as deref, because we want to dereference the box before we take our reference. That way we can get the value inside of it. So now we want to implement in the iterator trait for our iter type. And remember, we need to specify our lifetimes in all these. So now we have that set up. We can now begin implementing in the logic for our iter type. So it's going to look very similar to what we already did. So we'll say type item is equal to, and again, since it is a reference, we need to include the lifetime in this case. And now what we can do here is going to be, again, very similar to what we did above. So we'll say reference self, where we return an option to our item. And now we say self.next.take, and now we want to map it on our node. And inside of here we will say self.next equals node.next.as deref. And then we return a reference to our node element. So a lot of this probably looks really similar to some code that we have done above, which you can see here is equivalent to what we did here for pop. So a lot of this has already been pretty much done for us. So implementing this in actually wasn't too bad for us. So what we need to do now is add in our test cases to make sure that our iterators work as we would like for them to. So we need to do our test. And so in here we will test our iterators out. So we will say let mute list is equal to a new list, and now we will push in some values. And now we will create our iterator. So let mute iter equal to list dot iter, and now we will assert equals on iter.next, and we expect the value of sum with a reference to 3 to be printed out, because we're starting at the head, and if we iter again we expect 2 to be, and now if we do it one more time we expect 1, and then lastly we would anticipate none being printed out, or being returned, excuse me. So let's run cargo test and see what we have. So it says we cannot, it helps if I add the semicolon again, and if we run this we see that our iterator test passed successfully. So we have created in 2 iterators. We did our iter and we also did our into iter, which are 2 different types that are implementing in the iterator trait. So in the next lecture we will go over the assignment for the iter mute iterator. Now that we have gone over 2 implementations for a couple different iterators, I want you to take some time to implement the mutable iterator known as iter mute. As you might have noticed, when we were implementing these two iterators in, their setup is very similar, so the same will hold true for our mutable iterator. Don't forget, you need to pass in a parameter here, a return type, and then add in your code down here, as well as creating your struct and then also implementing in the iter trait for itermute. So take some time to give this a whirl, and then in the next lecture we will go over my solution. I hope you enjoyed that assignment and that you were able to successfully complete it. We will now go over my solution for the assignment. So the first thing that I want to do is create my struct. So we'll say pub struct iter mute. We need to pass in a lifetime, and in here we will say next option, and since we are going to have a reference, we need to specify our lifetime, which is why we gave it at the up here with the struct node t, and now our struct is good. So now we can come back down here. We know that we need to pass in a mutable reference to ourself, and our return type is going to be an iter mute of type t. And what we will do here is we will return an iter mute, where our next value is self.head, but instead of as deref, we do as deref mute. And that's the only difference between our iterator here and our mutable iterator. We just needed to use as dereference mutable versus as dereference. So now we can come down here and we can do our implementation block on our iterator for iter mute. And as you might be guessing, it is going to be very similar to what we did up here. So we can actually take this code, we can copy and paste it, and what we're going to change in here is we'll make this as dereference mute, and we will also make our type item mutable as well. So we see that we have an error. What do we have? Mismatch types, expected, option and mute t, found, option and t. And that is because we need to make our return type mutable as well. So now that we have our iter mute implemented in, we need to test it out to make sure that it works properly. So we will call our test function iter mute. We will give it the test attribute, and now we will say let mutable list equals list new list dot push. We will push in 3 values again, and we will push in our normal 1, 2, and 3. Now we will create our mutable iterator using list dot iter mute, and we will assert equals that iter next returns sum and mute 3, because we expect our values to be returned as a mutable reference. So if we execute this 2 more times, we would expect our next value to be a mutable 2 and a mutable 1. So now if we run our test, we see that all 4 of our tests are passing. So our implementation for iter mute is working correctly. So hopefully you were able to get this assignment. If you have any questions, please feel free to ask me in the Q&A section, and I will see you in the next lecture.